Okay, so welcome back to our last lecture on amplitudes from the nodal sphere. And where we stopped in the last lecture was that we finally made it down actually to the Riemann sphere after calculating our amplitudes on the torus. And remember, this was a residue theorem that allowed us to do so. Now, what we want to do in this lecture is what we did in all of last lecture, is we just looked at RNS, at the RNS ambitwistor string, and this gave us type 2 supergravity. And we did this for a very good reason, which is that we didn't know how to handle the non-physical gravitational modes in the other theories. So what we want to do now is, the first thing is to see whether on the nodal sphere, and with some of the additional background and tools that we have from before, we can also understand some other theories. In particular, this might be less than 10 dimensions, and it would hopefully include super Young-Mills or some other theories that we're interested in. The other thing that we need to do is, if you were astute, you might have already noticed this, but we should really look at what integrand representation we're landing on here on the nodal sphere. And this is actually going to be the main part of what we're going to do today. And then at the end, I'm going to end with some miscellaneous topics. This is not necessarily picked by importance or anything, mostly by what I'm interested in, what I would like to tell you about. And in particular, at the end, in my miscellaneous topics, we're going to finally talk about nodal spheres beyond one loop as well. Not about the higher genus correlators up here, but at least down here, we will get to talk about it. Okay, that's the plan. Let us dive in. So just to recall, the reason we didn't do anything on the torus with, say, the heterotic ambitwistor string is that the spectrum contained higher order gravitational modes. And so it would be really hard, or at least it might not be straightforward, to project those out. However, now we're on the Riemann sphere, or the nodal sphere, we have a much better grasp of, we have much more experience playing around with these things. So in particular, our idea is going to be to use again something like the double copy relations, but now the ones on the world sheet. And we don't want to do a double copy because we have type 2 supergravity. Ironically, this is the one we found most easiest. So instead, what we want to do is a single copy. Okay, to do that, this is going to be for super Young-Mills. To do that, let's look again just briefly at what the integrand looked like. So I've abbreviated all the measure into this d mu n1, where the 1 here is meant to remind you we are on the nodal sphere, but let me stress, this is the measure on the nodal sphere. We're done with the torus. We're not going to talk about higher genus anymore for the foreseeable future. So remember, what we found was that there was a sum over NS states, and I apologize, I forgot a factor here. There was a sigma plus minus squared down here. And then the Riemann sector. Now, the first part that we can notice is that it seems really straightforward to decompose this into 2 bits. And in particular, we can decompose it here into a part that I'm going to just call INS1, which will just contain all NS states running in the loop. Now, we can also really easily change the dimension here, because remember, the only part where this came in was in the epsilon, when the sum over the polarization states are here, there was an epsilon.epsilon component, and that gave us a d minus 2. So just by changing that, we know where all the dimension dependence of this sits. Now, in the Riemann part, the only thing I did here is I've changed this CD, this coefficient of 8 here, to a CD. And that is meant to indicate that clearly when we change dimensionality of this, we should be a bit more careful with whether we pick up different coefficients here. But we can do so. And in fact, it's really easy to see what the coefficients should be in other dimensions just by reducing the 10D Majorani Weyl spinors that give us the 8 here into lower dimensions, just decomposing them. And so we find that if you reduce that to 8D, you will just find a Weyl spinor, so that's also 8. In 6, you will find that this gives you, just decomposing your 1 10D Majorana Weyl, just gives you 4 6D symplectic Weyl spinors. So that means you should just divide this by 4, which gives you 2. And similarly for C4, if you could decompose this into 4-dimensional objects, you find 4 4D Majorana spinors. So that also gives you a factor of 2. So now I've promoted our SUSY factor here, that was just the one that we had in 10 dimensions, into something that is now valid in an arbitrary dimension, D, where D is smaller or equal than 10, obviously. Now, with that, it's clear that we can write down different gravitational theories, NS and S gravity, and in arbitrary dimensions, well, 10, 8, 6, and 4 that I've given you here. But if we want to also include Yang-Mills theories, we'll need to make use of this double copy idea, or in this case, the single copy. And what we're missing is clearly a color factor. So what possible color factor can we write on the torus? Who knows? I don't know how to write a color factor on the torus. But on a nodal sphere, there's really only one object that makes sense to write. Let's start by something that looks like the tree level, but with 2 additional lengths. So we're going to write, so let me be specific, this is at 1 loop, we're going to sum here over alpha in Sn rather than Sn minus 2. And we're going to have a C alpha at 1 loop here, which is just going to be our color dependence, and we're just going to sum over all denominator Park-Taylor factors as before. So I've literally written down the equivalent of what we would have written at tree level with n plus 2 points. And the only thing I have to be careful with is this numerator factor that encodes our color structure. But it's also clear what we should do for that, because what can it be? It can only be the tree level one for 2 with 2 additional particles, plus and minus. But of course, we should trace over the loop, what color runs through the loop. So I've just included the delta function here. There's nothing else this can be. Now, that's well said, but let me maybe include a picture of what I've done just so that this becomes a little bit more clear. So I've written the color factor in the KK or half ladder basis, where I've put plus and minus at the end. And then what I'm doing with the trace here with the delta is just that I'm gluing these 2 back together. Now, graphically at least, I hope it should be clear that this then corresponds to, well, just glue it together, and hopefully it's clear that this will correspond to something of this shape. So where here is alpha 1 up to alpha n, and this is my plus and minus that I've glued together. So hopefully it's clear that this will give you one loop diagrams. Now, let me just assemble these components. just to be precise about this, this is this is now, if you want a one loop, and I shouldn't call it double copy, but it's now the single copy. On the world sheet. This tells us that we can now write from this, for example, bi-adjoint scalar amplitudes by just using two of these color factors at one loop. And we similarly find super Young-Mills from just using the one SUSY factor. And remember, we can use this in d dimensions and one color factor. And by just using the NS part instead for Young-Mills, NS versus not NS, or just pure Young-Mills makes no difference. So we can also write down the integrand for pure Young-Mills actually at one loop, only at one loop, by just using the NS part here and the color factor here. Now, just for completeness, let me include what we already knew, that the supergravity one came out from two of these SUSY factors, where as usual my tilde just says replace epsilon by epsilon tilde, so that you have the full freedom there. But we can also now write NS gravity by just restricting this to the NS part. Oh, sorry. You could work harder in 4 dimensions and also extract pure gravity, but this is only true in 4 dimensions, where you can relatively easily extract out the dilaton and the axion. But let me not give this formula, because it requires some more identifications that is really relying on the string analysis to identify the scalar modes. But let me just mention that in 4D, this can be done. So just to summarize this, in some sense, we've really had a free lunch here. Of course, it's not entirely free. It requires the work of a lot of people before us. But we started out just reducing type 2 supergravity to the Riemann sphere, just finding a simpler formula for that. And then magically, we found that the double copy relations and the single copy relations allowed us to write down formulas instead for a whole range of theories. Now, that's wonderful, but at this point you should really ask, well, did we actually have to go through the full calculation on the torus? Especially given that we find so many amplitudes here that, or the integrands at least, for all of these amplitudes that come directly from the nodal sphere and that we didn't find on the torus. Couldn't we have gotten this a little bit more easily? Can we find these nodal sphere amplitudes, calculate them without going to the torus? And the answer is yes. It's a really pretty construction that we'll explore by David Skinner and Kai Röhrig, I should say. And we'll explore this. It's one of the voluntary exercises on the homework, so you will see this in a little bit more detail. But the idea is the following. The idea is that in these models, we've discussed the BRST cohomology, and we found all local operators in this BRST cohomology. But the idea is that in these models, there exists a gluing operator that encodes the target space propagator. Now you could see that this is a really useful idea. So for example, you could recover the BCFW recursion relations on the world sheet from this by connecting two spheres. And here's my target space propagator as so, by including a gluing operator between two different Riemann surfaces. However, it turns out that you can also insert this gluing operator on a single Riemann surface. And when you do so, you do indeed find directly these amplitudes on the nodal sphere. Now, just to mention the idea of this, as I said, we will explore this in more detail in the homework, but the main idea for the construction is the following. Now, we know that it cannot be both BRST invariant and local, because that's the spectrum. You cannot encode an off-shell object as being both BRST invariant and local. So the idea is we want to preserve BRST invariance, but we want to be, but because we want to preserve that, it must be non-local. Okay, so what can we then write down for this object? So I'm going to call this this gluing operator delta. And let's say we wanted to construct this. Now, clearly, we want sigma plus and sigma minus to be special. So I'm going to write these as arguments. But remember, it's a non-local object, and it will also not be a bilocal object. So it will depend, despite the fact that I write it like this, you don't think of this as bilocal. So what does this have to be? Now, clearly, we know roughly what we want to write. We want a ddl over L squared. This will clearly be necessary to be a target space propagator. And then what we want is a sum over states, clearly. We've seen this in all of our constructions. And then two things that should look roughly like vertex operators. Roughly. So I'm going to put tildes over them because they should be off-shell. And so this means in particular that we want to construct these such that v tilde of sigma plus or minus as L square is 0 just becomes a standard vertex operator at that point. And in fact, what we'll see is on the problem sheet is that it's okay to just take the trivial extension, meaning write down the same object, but just take L squared to be non-zero. Now, this can't be everything, because this object, as I've written it, is not BRST invariant. And so clearly what we should include is another factor, which is whatever is required to make this BRST invariant. So this is the factor, and in fact, you will find this in the homework, to make this BRST invariant. And what we'll prove is that there is a form for this that is relatively simple, which is just an exponential of an integral over L square over 2 omega plus minus square, and I'm missing a factor of E tilde. Remember where E tilde is our Lagrange multiplier that enforces P square is 0. So you can see what this does, morally at least. Morally, this will modify our BRST operator to not set P squared to 0, but P square minus L squared to 0, L square omega plus minus square, which is exactly what we found our scattering equations at one loop should be doing on the nodal sphere. Okay, so we'll explore this a bit more on in the homework, but at one loop, this is the answer. We can calculate amplitude from the nodal sphere with this gluing operator approach. I should say that it's not clear how to extend this beyond one loop. And if you have smart ideas, or any ideas for that matter, after the end of this, just think about it and publish it, because it's genuinely an open question right now, though I should say I don't think it's an easy question. Okay, so moving on now, there's something really important that we need to talk about, which is which we could have spotted already in what we said before, which is that there's something strange with the integrand representation that we have that we should really understand and think about. And let me just spell out what it is. Let's look at our nodal sphere representation that I've pinned down here. And in particular, I've spelled out the scattering equations as well. including their explicit form. Now, what I want you to notice is the L dependence, the dependence on the loop momentum. So we have an L square here. That's good. But the rest, remember, of course, the integrand itself might have some complicated dependence, but all the pole structure comes from the scattering equations. So there is an L square here, but that is really only subtracting out the L square that is in the P square. So in particular, in our scattering equations, they only depend on L in a linear way. There's no L square terms anymore. So that leaves us really with a puzzle, because it looks naively, even from what I've just told you, as though our integrand, if we were calculating out, would now take the form, as I said, this tilde is just, this will take that form of some numerator factor and then some L square, and then some product over F1 L up to some poles here, but all of these will be linear in L. That doesn't look like a standard Feynman propagator representation. That in fact, it is not. For a Feynman propagator, we would like something like L plus Ki square. That's really not what we're getting. Or it looks like that's not what we're getting. And in fact, we can make this precise. And it's a really, if you do the homework, it's a really straightforward extension that you should briefly convince yourself of. This is what we started the whole discussion with, that we know that the boundary of the moduli space has a correspondence via the scattering equations to some pole becoming smaller, going to 0. And what you should convince yourself of is that these correspond to the following poles. This one down here, so these are again the scattering equations, and in this case, the ones at one loop. In this case down here, everything is fine. This is like the tree level ones, and we just find the pole Ki square becoming small. But in this configuration, where we split the two nodal points, what we actually find is that the pole takes the form 2L dot Ki plus Ki square. So really no L square dependence there. Now, meaning heuristically at least, our IN1, we can now be more precise, then starts to look like a sum over terms over n divided by L square, and then a product over things that look like 2L dot Ki plus Ki square. Are we just wrong? Is this, this should be really troubling. Now, of course we're not, otherwise I wouldn't be giving these lectures or anything like that. This is what is known as a linear representation of the loop integrand, but we should talk about how this relates to the standard representation. In fact, it's relatively easy to go from the standard Feynman propagator representation to this linear representation. The other way around is generally or generically not that easy. So what we're going to discuss here is how to go that way around. So for that, let's just look at a standard Feynman propagator representation, and I'm going to write this as, so we have some Feynman propagators here, and I'm going to write this as some numerator factor that could depend on L, and then some denominator factor, sorry, capital I here, so that you can't, it's not particles here, di, where my di is just Ki plus L all square, and Ki is just the sum over some subset I of the external momenta. Now, note that there could be some factors that just look like ki square with just external particles, but I'm just going to absorb them into the numerator for this discussion right now. They are, of course, not strictly speaking a numerator factor, but it just to keep notation compact here. Now, how to go to the linear representation? We do this from the following. We're going to use a residue theorem. You've seen a lot of residue theorems in my lectures, so you're now experts on all of these. And it's a particularly simple one. So we're going to shift L to L plus eta, but we're going to pick eta to just be higher dimensional and just have components in the higher dimensions. So in particular, this means that L dot eta and Ki dot eta for all external particles I is going to be 0. And so really the only invariant, the new variable here is going to be eta squared, which I'm going to call Z from now on. Now then, of course, our Feynman parameter one is then the one at Z equals 0. And so we can write this out, of course, as usual, as dz over z. And now we have here an n. And actually, let me upgrade this here, because I want to write also the L square terms, because they're going to be relevant of L and L square plus z now, just to keep this explicit. And then a product here, down here, running over di plus z. Notice we have always a plus z here because all of them are of the form ki plus L squared. Now, it's straightforward to apply the residue theorem here. So we just find a minus sum over I equals 1 to m, where this, runs up to m here. And then the residue at z equals minus di, and if I can evaluate that immediately right now, that gives us L square minus di here, and then down here we find a pole di, and then a product over all j not equal to I, dj minus di. And now notice this term is quadratic in L. This term is linear in L. Now, clearly, we're not quite home yet. We want to make we want to make contact with the representations that we found on the last slide. Remember, we always have this factor of 1 over L square, but you should be able to see now that what we want to do is now just shift each term in the loop momentum L respectively, such that we find an expression where we can pull out the 1 over L square. So in particular, that means we shift, sorry, I didn't plan this well. We now want to shift L to L minus Ki in each terms respectively. And then what we will find, sorry, let me put a tilde over this here, so that we are just so that we're mindful that this only holds under the loop integral, and that we'll have to be careful with this. We find a 1 over L squared, sorry, this canceled actually the sign here. And then a sum over terms that again runs over I equals 1 to m. We now can pull out the L square. And then there's now some numerator dependence here that you can fill in at your leisure if you want, minus 2L dot Ki plus Ki square. And all the factors in the denominator now take the form that we found, to L dot Kj plus Kj square, where the j here, you have to be a bit careful. This is Kj minus Ki, so there's some shifts, but it's straightforward to see that this comes out in this format. Now, that's great. So this is the representation we land on, so we don't have to worry about this. This is actually a valid representation of the integrand. We just have to be mindful that some things might look a bit different in this representation. And in particular, while it's easy to go from the standard representation to this one, going back is not always that straightforward. Now, one useful or one comment that I want to make on this, maybe just briefly in view of time, is that there's something closely related to this Integrand representation, which is known as a Q-cut decomposition. And in fact, Jake is the expert. So if you have questions, you have experts directly in your audience, not audience, but in the lecturer list. And that allows you to write the integrand, IN1, as a sum over two now on-shell three-level amplitudes with factors L squared to L dot Ki plus Ki squared in the denominator. And in fact, what we did on the last slide to get to the representation we were discussing is the first step in deriving this Q-cut decomposition. And then there's a second step to get to this, which is the following. You have to also do a residue theorem in rescaling L to alpha L. And so you have a residue theorem in the integrand depending now on alpha L over alpha minus 1. Now, I won't spell this out in detail, but when you do, you find that indeed only 3 amplitudes contribute here. This is going to be something really useful for generalizing these representations to higher loop order. And it's also the representation that you would use if you wanted to prove the amplitudes that I've been writing down. In particular, it's easier to do this for the non-supersymmetric ones because otherwise you'll have to handle fermions. But if you were to prove the formulas for the integrands that I gave to you on the last slides, you would do something very similar to what you'll do on your homework for tree level, but matching to this Q-cut decomposition of the amplitude. Okay, so while this may be a little bit abstract from the residue theorem, let's just do 2 examples, and I'm going to do 2 really basic examples because more complicated examples don't fit on slides. Or are not, I can't write fast enough to fit them on slides, I should say. So the first one is a really simple one, which is the observation that for trivial numerators, n equals 1, this just becomes a partial fraction identity. And you can see this as follows. So just run through the same argument with just 1 in the numerator. So I have the same sum di here. Now, when you run through this, just recycle the formula from the last slide, 2 slides ago, you find the sum from I equals 1 to m, 1 over di product dj minus di. And this is just partial fractioning. This is something that is really easy to check. So I haven't done the shift in the loop momentum yet, but just to convince you that this is something you could actually do really easily. And in cases like the biogiant scalar, you don't need the complicated residue theorem that well, it's not that complicated, but you don't actually need the full argument. In simple cases where the numerators are trivial, you can just use partial fraction identities and then some shift in the loop momentum. Now to see this in full practice, let's do the really simple example of one off-shell bubble. So we start out with 1 over L plus K square. And the reason I wrote down the partial fraction identity for you above, let me actually do this down here to have a bit more space. So first we use the partial fraction identity. We can see that there's 2 terms there. One from where our first di here, sorry, and I'm missing an L square here. One where our di here is just the L square term, then we find an L square times 2L dot K plus K square, just calculating the dj plus di up here. And then there's a second term with L plus K square, and then subtracting L plus K square from L square, we find minus 2L dot K plus K square. Now, shifting the loop momentum L to L minus k in the second term only. Well, the first term we can just recycle. The first term is 1 over L square, and then with the 2L dot k plus k square. And then the second term gives us a plus 1 over just shift here. And if you shift L to L minus k, you find that minus 2L dot k survives, but instead of the plus, of course, I misspelled this inconveniently. Instead of the minus k square that we had up here, we find a plus k square. Now, this is the simplest possible example, but you hopefully can convince yourself that you could go through the same calculation for, say, a box, and it would be straightforward to do so. Now, the other point that I want to mention right now is that this is actually somewhat an instructive example, because it means that we don't find on-shell bubbles in this representation. They're automatically regulated here. Just take the limit as k squared goes to 0, and you can see that the two terms cancel against each other. So no bubbles in the external lengths in this representation. Okay, so in my last few minutes, I want to still tell you two things, which is various consequences that come in particular about once you understand this, that we land on a very special representation of this, or that are closely connected with this. Now, the first one is that we can make the double copy relations. Remember, we were using single copy to construct our integrands on the nodal sphere, but we can use the same trick as at tree level to make the relationship to the standard double copy, and in particular to BCJ numerators, explicit. It's very similar to what we do at the tree level. The Cn that I gave you was already, in fact, in the KK basis decomposition. So we had, remember, an alpha in Sn C alpha at one loop, over the Park-Taylor factors plus with ordering plus alpha minus. And very similarly, you can decompose the sum over Pfaffians into a same type of decomposition, into a KK decomposition with plus alpha minus here as Park-Taylor factors. And the numerators that you find up here, they're one loop. And then as before, this only holds on the scattering equations, I should say. And these are again BCJ numerators by the same argument as before. And in fact, they have a really simple representation. These BCJ numerators at one loop are just the same polarization sum here over the tree level BCJ representations that you find from expanding out the Pfaffian. Now, this is true. This gives you BCJ numerators for just the NS sector, but in fact, Ollie is the expert on how to generalize this to supersymmetric theories. Now, note, however, that these are BCJ numerators, not for the standard Feynman propagator representation of the integrand, but for the linear representation. And while you can always go from the standard representation to this linear representation, going back is not always straightforward, and going back will also not be guaranteed to produce BCJ numerators. The other way around is true. If you start with BCJ numerators in the standard representation and expand it into this linear representation, you will still have BCJ numerators. The other way around is not known how to do. So that leads us to a really important conclusion, which is that the double copy in this linear representation seems to be more general. Whether this is useful or not remains to be seen, but it's something important to keep in mind. Also, let me just make a comment that we'll get back to maybe briefly, which is the following. Let's say you didn't know what integrands to write down. You could take the definition that I gave here for the decomposition of the Pfaffian as a definition of what your integrands should be on the nodal sphere. If you know the BCJ numerators from somewhere else, you could then recover a more compact form of the full amplitude on the nodal sphere. Yeah, we'll briefly comment on how this is useful. Okay, so as advertised, the final thing that I want to briefly talk about with you is how you would generalize this beyond one loop. Now, we could very naturally propose the following. Now, just looking without diving further into this at what we found at one loop, the natural thing to write down would probably be something like this. Let me put a big question mark over this, but probably we would generalize this as follows. So we want a product over all L squared, where this runs from 1 to G. I apologize that I used the same label here, but this is now my label for the loop order. And then an integral over d mu n, d mu n G, where we'll be precise what we mean about this in a second, over the moduli space of Riemann, nodal Riemann spheres. Well, and particles, but we get 2G additional points from going to the nodal sphere. Okay, and then some integrand ing. Let me just mention briefly, this is clearly difficult to get. And you can see that maybe that's a one road into this would be to use a BCJ numerator expression that you know already, but in general, this will not be easy to find without doing an explicit calculation on a higher genus surface. Now, the important part that I didn't say is what we actually mean by this. And naively, we could say that we want to construct our scattering equations EA, let me put a question mark over this as well, as the residues at sigma A of some form PG, where I'm going to define this to be P square minus the sum over Li square omega I plus I minus square, where these are the differentials with simple poles at the nodal points, say for 1 plus 1 minus, at the nodal point sigma 1 plus and 1 minus, and then 2 plus and 2 minus would be the ones here. Where I should also say I've used the label A as 1 up to n, and then also 1 plus 1 minus up to G plus G minus. This would be an entirely reasonable conjecture to make, and it's not precise because we haven't put in the integrands here. But even before you get to any of this, you can just see that this is wrong. This doesn't work. And the reason it doesn't work is already in the basic structure that we wrote down. And the only thing we wrote down and were explicit about were these scattering equations. And the reason is that how you generalize the linear representation, remember the linear representation that we saw here that was looking like this, to higher loop order, doesn't just involve terms that look like L1 square and L2 square, say at 2 loops, but you also need to preserve terms of the form L1 plus L2 square, which we really don't do with these scattering equations. Now, we'll do this in great detail on the homework. It is much easier than it probably sounds right now. It is basically going through the same tree level analysis and making sure that we preserve the correct types of propagator poles. But let me tell you what is the actual answer. And in this case, for G equals 2. So this is still beyond one loop, but now true. so for G equals 2, what we should be writing instead is the following. We should be writing that IN, my 2 loop 1, is 1 over L1 square L2 square. So this is what we were writing before, and the M naught n plus 4 is also what we were writing before. And 2, where now my scattering equations take the following form. I want EA at 2 loops to be the residues at sigma A of a P2 that is now properly defined. Sorry, this will not fit. Properly defined as as follows. We still have the P square minus sum over I Li square omega I plus I minus square. This has to be there because otherwise the residues are not well defined. But we need an additional term here, which turns out to be L1 plus L2 square omega I plus omega, sorry, 1 plus 1 minus omega 2 plus 2 minus. So this is a really important change in the scattering equation. Now, this was actually not all. We did need another factor up here. Sorry, let me write this. I think I called this C2 on the problem sheet, where this C2 is a cross ratio just of the nodal points. So it's clear that you can't write something like this at one loop, for example, but these objects will play an important role from 2 loops onwards. Plus over sigma 1 plus 2 plus sigma 1 minus 2 minus. Sorry. Sigma 1 plus 1 minus sigma 2 plus 2 minus. Okay, let me give you the last detail that I didn't write out here, which is that the IN2, I don't actually want to give you this for n particles because that gets a bit messy, although it is known. But let's just look at this for 4 particles. Now, if you remember from Ollie or somewhere, there will always be, for 4 particles, we know that there will always be a factor of 4 here if I write this for type 2 supergravity right now, which just is proportional to the tree amplitude. So the tree amplitude, the tree sugra amplitude has the form of 4 over S12, S14, S13, so that defines it, but it's also straightforward to write this down. For example, for super young mills, if you factorize this into 2 components that are usually called kappa and kappa tilde, it's just traces of FF. And then there's 2 factors here that we need. The one is a Jacobian factor that comes from going from the higher genus to the nodal sphere. And the other one is I'm going to call Y2 and the full thing square, where this Y2 factor, J2 factor, sorry, let me write this first because this is just a Jacobian factor. This is straightforward. It's just sigma 1 plus 2 plus sigma 1 minus 2 minus sigma 1 plus 2 minus and sigma, which one do I not have? 1 minus 2 plus. So you can see that this just matches every nodal point with every other except for the ones that are sitting at the same node. And it's something that you can calculate will come out naturally from going from a higher genus Riemann surface to the nodal sphere. Now, the interesting part is that this Y2 here is something that you're actually familiar with if you've looked at the string calculations. This is the same, well, this is the degeneration limit of what you would also find in type 2 string theory after simplifying. And it takes the following form. One invariant way of writing it is that it's 1/3 S14 minus S13 times delta 1, 2, delta 3, 4, plus cyclic terms in 2, 3, 4, and let me change color before this gets too messy. I've defined the delta 1, 2, for example, as, let me write this compactly as an epsilon ij, omega I plus I minus of sigma 1, omega j plus j minus of sigma 2. Sorry, multiplied. So you can see this is just an antisymmetric 1 plus 1 minus of sigma 1, 2 plus 2 minus of sigma 2, minus the one where you switch the puncture, sigma 1 and sigma 2. That's really suggestive that this y2 comes out as the same as the string calculation. Now, just to wrap up in the last few minutes, let me make 2 comments on this. So the first one is that I've given you here the formula, but it can be derived from, well, a more complicated correlator calculation that matches the string calculations by Doka and Fong for genus 2. So this is something that's quite messy. It's a heroic work on genus 2 in the superstring. It's somewhat easier in the ambitwister string because there's no super Riemann surfaces, but still an involved calculation. And then after you've done that, it can be derived from a residue theorem. And actually, to be precise, it's 2 residue theorems. And there's additional subtleties in these residue theorems. But the idea is still that you map first with a residue theorem to a sum actually over nodal tori, and then by an additional residue theorem to a nodal sphere. And instead of going through any of these calculations with you, let's just go through very heuristic counting to make sure that we understand at least the basics of this, which is just that a moduli counting. So on the higher genus Riemann surface, we'll start out with 3g minus 3 moduli, which are the higher genus equivalent of the tau that we had at one loop. And at each order, we lose one of these moduli because we set it to 0, similar to our q to 0 in the residue theorem, at least if this all goes through. So what we end up then with is on the nodal sphere 2g minus 3 moduli, which is indeed the correct number of moduli modulo Nebius transformation. So we can see that this is the 2g nodal points modulo SL2. Okay, so the formula I gave you on the last slide can be entirely derived from this. But apart from the integrand, the y that I wrote here for you, there's actually good physics reasons for why to expect the various terms. And this is as follows. So if you generalize the linear representation that we did discuss in detail at one loop, and you will see how to do this on the problem sheet, you will find that the propagators in this representation, in the linear representation, are always of the form 2L dot Ki plus Ki square, but they do retain the form L1 plus L2 plus Ki square if both loop momenta are involved. So clearly that means we'll have to modify the scattering equation. Say we didn't know about the residue theorem, just from physics reasons. We know the scattering equations have to reproduce these terms. And indeed, you can see, there is a typo here that is an important typo, so I will fix this immediately. Because what we have to add here is in fact just L1 square plus L2 square. And you can see that these L1 square and L2 square terms are therefore really relevant. We have to somehow find them somewhere in the scattering equations to be able to produce the poles here in L1 plus L2 square correctly. Now, once we know that the scattering equations have this form, it's also easy to see why we expect in the end something like this cross ratio to come up. And the reason is the following. We can now just check what poles, so this was, if you want, 0.1, and now check what poles come out of the scattering equations. Now, just from a physical point of view, we would have constructed them, and indeed this is how you will approach them in the homework, to match these poles. But what we'll find is there are also unphysical poles. Well, the scattering equations also encode unphysical poles, and these unphysical poles are precisely cancelled by this factor of the cross ratio. Now, maybe let me just make one last comment. What if you didn't know the form of this Y2? Say you wanted to recover this just from entirely a physics approach without doing any calculation on the homogeneous surface. You could actually do this. I will not spell it out for you in detail, but you could use the BCJ numerators at two loops that are known at 4 points. Use the same in this representation. First, take the BCJ numerators, put them into a linear representation, which is straightforward by the procedure which we discussed, how to go from a linear standard Feynman propagator to the linear representation, and then promote them to a formula like this on the sphere, and you can match this to the full J2 Y2, and after simplifying, you would precisely recover this formula. So at 2 loops, 4 points, you could have recovered this whole formula on the nodal sphere just from the physical, just from some physical interpretation and from matching it to what you know an amplitude has to satisfy. In fact, that's very much the approach we'll take in the homework problem, because the calculation on the homogeneous surface is very messy. Now, let me also just mention that it is really tantalizing that this is the same as the string integrand, this Y2, especially on the homogeneous. This is precisely the same. But maybe that's something we could discuss more if you're interested in this in the discussion sessions, because it's very hard to make this. There's precise statements you can make, but there's no good understanding of this at this point. Now, to wrap this all up, let me just actually summarize for you both what we did and what is known about amplitudes from nodal or integrands from nodal Riemann surfaces. Now we've seen tree level, and sorry, I should first tell you. So what I've drawn here is on one axis I've put the loop order, so 1, 0, 1, 2, 3. So this here's just tree level, and then it goes up. And on the other axis I've put the genus, and obviously the upper half here you can't fill in because it goes. It's only well defined in the right lower triangle. So tree level, we've seen we have CHY, and we found a whole family of amplitudes there. And we understood quite well how to derive these from an ambitwistor string. Now, we've also discussed the torus, and in fact, here just for the RNS model, but we did find that once we go down to the nodal sphere, we have a whole family of models again. So here we found supergravity in d dimensions, we found super Young-Mills, and also other theories. And we do expect that you could indeed generalize this further beyond the ones that we discussed. It hasn't been done in detail, but it's relatively clear that the nodal operator procedure, the gluing operator, would generalize to other theories as well. Now, at 2 loops. I mentioned briefly that this can be done on the Hyot-Linus surface, and indeed, again, we only do this in the RNS model for type 2 supergravity. When you go through the residue calculation, you do find indeed these one nodal tori pictures, but as far as I know, no one is particularly interested in them except for as intermediate steps in your residue theorem. And then once you go down all the way to the nodal sphere, we again have formulas that we can work with and that are generalizable easily to n points. But let me just mention that in contrast to one loop, it is quite hard to generalize these formulas to theories with no supersymmetry. So we do have this for supergravity and super Young-Mills, but no, so remember here there's a dot, dot, dot. Here, I don't want to put a dot, dot, dot in. You can, but it's quite difficult. And one of the reasons for this is the linear representation that we have doesn't sit quite well with these non-supersymmetric theories. If you want, that's something that we can discuss, but it's something that is quite intricate. So I think it's fairer to say that we want to use this only for supergravity and super Young-Mills. And then actually very recently, we did notice that you can generalize this to 3 loops. And I should say, for all of these other things, the calculational pipeline went calculate in the model, and then if you're at Hyot-Linus, reduce down to the nodal sphere. Here, this was partially true, but strictly speaking, this was still mostly true. At 3 loops, calculations on a genus 3 Riemann surface are prohibitively difficult. So that is certainly not what happened. Instead, what was used were the BCJ numerators to produce a formula at 4 points. So if I don't write anything for any points, but here only for 4 points on the 3 nodal sphere. And then there exists a conjecture of how to lift this to a formula, at least for the ambitwistor string, for a Hyot-Linus surface. Now, the tantalizing bit here is, of course, that because we observed the correspondence between the 4-point integrands and in the ambitwistor string for the RNS model and the superstring, that it's easy to conjecture that this is the same as the string one, but that's certainly at this point very much a conjecture and nothing that has been proven. Okay, so hopefully in all of this, I've given you plenty to think about. I've hopefully given you a little bit of a taste for the different aspects of the worldsheet model underlying these nodal representations. I hope there was a bit of everything. So I try to include both the CFT aspects, but also quite physical or physics-oriented aspects. Yeah, so I hope you enjoyed the lectures, and I'm looking forward to meeting you all in the discussion sessions. Thank you.